So I guess our next speaker is Disha Proxy for Mike Thompson, and the the topic is well, Mike Thompson's from OpenHW Group. He's which is a not-for-profit global organization driven by its members and individual contributors, where hardware and software designers collaborate in the development of open source cores, related IP, tools, and software. Okay. OpenHW provides an infrastructure for hosting high-quality open source hardware developments in line with industry best practices. Mike is the Director of Engineering in charge of the Verification Task Group, and the title of this talk is Extending riscv to Suit Your Specific Needs.
So as Mike said, the topic of my presentation today is something that we call Core5-dv. It's an extension of the CHIPS Alliance riscv-dv, which is a component of our UVM environment. And what we're going to be talking about today is how to use the riscv-dv to target your specific core, because that's a big challenge in using this IP. Next slide, please. So these slides are part of a larger set of slides that are publicly available. Everything that we do in the OpenHW Group is open source. So if you're interested in looking at into this in more detail, let me know. The focus of this presentation is developing and running tests. And specifically, we're going to talk about the CHIPS Alliance riscv-dv test program generator and how we use it in our UVM environment. Next slide, please. Okay, so this is our verification environment. We call it Core5 We call everything Core5 something in the OpenHW Group. There's a lot here, and I'm not going to go through it all in great detail. The big box on the left-hand side is the UVM environment, and in that UVM environment, we run a reference model of the core and the RTL of the core, and both of these models are running exactly the same test program, and we compare the architectural state of the core and the reference model as each instruction is retired. So that's how the UVM environment works. The question is, where does this test program comes? And if you can just click one more time, Mike, on the left-hand side, you'll see the topic of this presentation, and this is the CHIPS Alliance riscv-dv test program generator. And this is a tool that we use to generate programs randomly. It's a UVM component. Next slide. Okay, so this is going to be a mouthful. Test cases, test programs, and tests. You probably already know that UVM makes a distinction between a test case and a test. A test case is a UVM class, and a test is just running that class to produce a specific simulation with specific solutions to the random variables. If you can click one more time, Mike. We're talking today about the test program. So this is machine code. This is not a UVM concept. This is a concept from our test bench. This is a machine code program that runs on the simulated model of the core, either the RTL or the reference model. So we're talking about where do test programs come from? Next slide. Okay, a little bit more about test programs. The device under test in our environment is the Core5 processor. Core5 is our branding for the family of open source RISC-V cores that we produce. And when you're developing a processor core, it's probably not a surprise that test programs are the primary source of stimulus for the DUT. We can write these by hand in C or in RISC-V assembler. If you want to write a test program by hand using your favorite editor and then run it through the cross compiler to come up with the machine code, you can do that. And we do have a set of manually written test programs that do a reasonable job of exercising the core. But if you're going to be serious about verification and close your functional and code coverage, you're going to need a lot more stimulus. So we rely very heavily on the on riscv-dv from the CHIPS Alliance team. Typically, to close coverage, we're looking at typically tens, maybe hundreds of thousands of test runs. And we're certainly not going to generate that many test programs by hand. So automatic generation of a test program is key to the operation of our verification environment. Next slide. There are other sources of stimulus in an environment, and I want to make it clear that those are important, but not really the fundamental topic that we're talking about today. So most of our cores will support debug. So we have a UVM agent that generates debug requests. We have a UVM agent that generates interrupts. We have UVM agents that generate memory bus errors. Those are all very important aspects, but they're really independent of the test program that is running. A test program usually does not know if it is going to be interrupted. And that's an important thing. There are other aspects of a simulation that do impact a test program. For example, something we call the core configuration. The simplest example of that is the address of the first instruction fetched. So everything in the environment, so the test program generator, the cross-compiler tool chain, and the actual system Verilog test bench all need to know and all need to agree on what that address is. Otherwise, things go south in a hurry. So you need to be able to control the operation of the generator to produce the starting address that the RTL expects. There are other aspects, including the execution environment interface and the application binary interface. The RTL test bench and the generator need to be aligned on these things. Next slide. Whoops, there we go. So riscv-dv is impacted by all of these things, but in Core5 it can't control any of it. So how do we control that? And we'll be talking a lot about that in the next few slides. Next slide. I get this question a lot, so I thought I'd answer it here. Why do we use riscv-dv? And the first answer is we needed to have some tool that would automatically generate test programs for us. Otherwise, we would be writing test programs for the next 50 years and not actually verifying our cores. We did look at several different options. riscv-dv was adopted for several reasons. The first is it was written in system Verilog UVM. This was an important consideration for us because our test bench is written that way. We did a preliminary analysis, and it looked relatively easy to use, and it looked like it was relatively stable. Of the three options we considered, it was the best documented. And I'll be honest with you, the backing of Google, this thing was originally developed by Google, and the feeling in the community was, well, if Google is behind it, it must be good. And that is both true and not true at the same time. So those were the reasons that we adopted it. And it turns out it was a good decision. We've been very happy with it. Next slide. Okay, so important things to know about riscv-dv. It is, as I've said before, written in system Verilog with UVM. It is implemented as a set of UVM objects. That is different than a UVM component, and this is a fundamental problem with it that I would like to fix one day. Randomization is controlled by a set of system Verilog plus args. So I'm sure you've used these before. This is not exactly the way UVM likes to constrain things, but it is the way that Google decided to implement. It is dependent on a largely undocumented execution environment interface. And this has been a source of frustration for the team, because the only way to understand the execution environment is to read the code. It's not documented anywhere. And it's packaged with a run script that is implemented in Python that is quite popular with some people in the RISC-V space. Next slide. Okay, so that's about riscv-dv. I want to talk about how we use it. You see on the little graphic on the right-hand side, we've got a blue box that I'm calling riscv-dv, and around it is a green box that we call core5dv. So we don't use riscv-dv out of the box. For example, the first thing we don't use at all are the riscv-dv run scripts. We use a set of make-files that handle cloning, compiling, and running of riscv-dv, all as a set of make-file targets, and we do that because we've extended riscv-dv so much. All of our customizations are implemented as system Verilog class extensions. And so we call these class extensions core5dv. Typically, core5dv will be core specific. So far, we've verified or are verifying 7 different cores, and each core is unique in its own way. And so core5dv tends to be rather specific to the core we're developing. An important thing to remember here is to understand here is that we do not modify riscv-dv in any way. We extend its behavior using the object-oriented programming model supported by System Verilog. We don't edit any of the code in riscv-dv. We just extend its behavior to either change it or to augment it in some way. We also give back anything that we feel would be generally useful to the open source community. We contribute back to the CHIPS Alliance team. There's several pull requests that have been accepted from the open hardware community in riscv-dv today. Next slide. Whoops. Just wanted to emphasize that part, that the customization are implemented as System Verilog class extensions. Sorry. Next slide. Okay, so let's get into the details of how we do this. Recall that core5dv is a set of class extensions that are specific, class extensions of specific classes in riscv-dv. riscv-dv uses a YAML formatted configuration file. We have adopted this verbatim and we just expand on it. So if you've looked at riscv-dv in any way, this little code snippet on the lower right hand side will be somewhat familiar. Our scriptware processes this and uses this to compile core5dv, which then compiles riscv-dv, and then run riscv-dv using these plus args as runtime options. Next slide. So that's how we control it. How do we change it? This ranges from very trivial to very complex. On your right-hand side is a code snippet of probably the most trivial extension that we've done here. So all the extensions are done as class extensions of an existing riscv-dv extension. And these extensions all exist for a reason. So some of them are to improve functional coverage, some of them are to target specific code coverage, others are to integrate the environment. Next slide. I'll go through this quickly. There are some really great examples of core5dv exceptions. The biggest one is to overload that setup code that I was talking about to make it run with our execution environment as opposed to the default undocumented execution environment in riscv-dv. We've also got support for core5 specific instruction sets. Next slide. Okay, just to wrap this up. riscv-dv is a constrained random System Verilog UVM instruction stream generator. We've used it successfully for about 4 years over about 7 cores, but we don't use it out of the box. We use System Verilog class extensions to provide the implementation that we're looking for, and we call that core5dv. Next slide. Thanks for your attention, and I'm sorry that I went a little bit over time.
No problem. Thanks, Mike. Yeah, and apologies for any issues at the start there. Are there any questions for Mike? By the way, we use this ourselves. It's a very good environment if you want to do constrained random verification of RISC-V cores, and we use it for SoC as well, actually. Okay, one question from the back, Mike, and then we'll move to our last speaker.
Okay.
Just introduce yourself.
Hello, I'm Miran. I'm an FPGA engineer. What does the development team for the OpenHW Group look like, and can anyone get involved?
So I'll answer your second question first. Yes, anyone in the world can join, and the development team is pretty diverse. It's made up of people from industry, so companies like NXP, Silicon Labs, Dolphin Design, TELUS, Cirrus Logic, 10X engineers. Organizations all over the world are participating. And we've got it depends on the interest of the team. Some companies will contribute design engineers to a specific project. Most of us are involved in verification because that's the biggest activity. We also have a number of contributors from universities. You wouldn't be surprised to hear that ETH Zurich is a strong participant. They're very big in RISC-V. And we do have some individual contributors, probably about a half a dozen people that just contribute to open source development on their own.
Brilliant. Thanks, Mike. University of Southampton members as well, I think.
Yes, they are. Absolutely. Yeah.
Good.
Yeah. So if you're interested in knowing more, go to openhardwaregroup.org or just reach out to me directly, and I can give you way more information than you have time to read.
I can fully recommend the environment. It's very useful. We find it very useful. Okay. Thank you very much, Mike.